So this time I'm going to be talking about transformers, kind of the backbone of most implementations, not only in natural language processing, but also, a wide variety of other things as well. And I'm going to be talking both about transformers as they were originally conceived and implemented in 2017, and also some modifications that people make to transformers today to make them work much better in kind of modern language models such as LLaMA. So I'll talk about both of those at the same time, please. So as a quick reminder, I just want to review the attention from last time very quickly. And basically, if you remember attention, there were two varieties of attention. One was cross attention, where you attend to another sentence, basically, or another sequence. So you have one sequence that serves as your keys that you are attending to, and one sequence that serves as your queries, the things that you are using to attend to the sequence of keys. And so you can do that for every element in the query vector, attending to every element in the key vector. And the other alternative is self-attention, where you are attending to the same sequence. So basically, you're guaranteed that the queries and the keys correspond to the same sequence. And so that's really the only difference between self-attention and cross-attention. Transformer-based models use either self-attention or they use self-attention and cross-attention. So I'll talk a little bit about two different types of transformer-based models that use both of those. And the way we calculated attention was basically by using the query vectors, taking all of the key vectors, and for each query key pair, we would calculate the weight between them like this. Then we would normalize it by using the softmax to make sure they all add up to 1 and are between 0 and 1. And then based on that, we took the value vectors and we multiplied in these attention weights, and we got a final vector for that. So a single query vector would result in a single value vector is the output. So that's just the review to get everybody's mind working, allow everybody to come into the room. And so now I'd like to jump into the new content of talking about how transformers work. In transformers were proposed in the paper "Attention is All You Need" by Vaswani et al. In 2017. When this paper came out, it was kind of already clear to me that this was going to be a big thing, soon after the paper came out. And it actually has turned out to be a very big thing, of course. But basically when it came out, it was a sequence model, a model that could generate sequences based entirely on attention. And so this is in contrast to what came before it, which is like they would have an RNN-based encoder, and then they would only use attention for cross attention. So all of the blocks in the encoder up until this point, these would all be RNN-based blocks. And then they would have a decoder over here, maybe also consisting of RNNs. Actually, this could be a bidirectional RNN, for example. And this could be a unidirectional RNN. And then they would only use attention for the cross-attention part here. So this would be attention. And so what the transformer did is it basically said, we're going to remove the RNN as the sequence modeling, and we're going to replace this all with self-attention. So hence the name "Attention is All You Need." So they removed all of the other sequence modeling components other than attention. At the time the paper came out, it gave strong results on machine translation, and of course now it gives strong results on everything. Another really important thing is it's fast, and it only consists of matrix multiplications. And so this is really important for the same reason that I mentioned last class, which is that RNNs are kind of bottlenecked by the fact that you have to wait for the calculation from the previous state before you can calculate the next one. Transformers, you don't have to do that. So it makes it much faster. And actually, I would argue that's probably a bigger reason why they became very popular than like that transformers are a better modeling methodology or anything like that. I think it's actually mostly due to them being fast. So I'm going to go through two types of transformers, specifically encoder-decoder transformers. And these are used in models such as T5 and BART. And T5 is actually still reasonably widely used in some applications. And also decoder-only models. And these are things like GPT and LLaMa. And this is used kind of most widely right now. Most of the new language models coming out are decoder-only models. So here are the architecture diagrams between them. And what you can see is a decoder-only model only has a single model here, where the encoder-decoder model has an encoder and a decoder like this. So the way the blocks of the way the transformer works is you have an input embedding, you have something called positional encodings, which I'll talk about a bit. Then you have multi-head attention blocks, and these multi-head attention blocks are followed by feed-forward blocks. So the multi-head attention blocks are basically doing attention. The feed-forward blocks are basically doing extraction of combination features to kind of mix together the different features from the calculated by the attention. And then in a decoder-only model, that's all you have. And then in an encoder-decoder model, you also have something like this, where you have masked multi-head attention to calculate kind of in place of the RNN here. And then you have this multi-head attention here in place of the cross attention here. And then you also have the feed-forward network. And I'm going to go through each one of these in detail, but that's just kind of the general structure. And so I mentioned that like encoder-decoder models were widely used in T5. This was also the original transformer paper had this thing here, this architecture here. This is a little bit newer. So why would you pick one or the other? T5 and BART, basically, they picked this one kind of partly out of tradition, but also partly out of for things where you definitely have like a clear input-output structure, right? So it's like, I want to take in a summary, or I want to take in a document. That's my input. I want to generate a summary. Or I want to take in an English sentence, and I want to generate a Japanese sentence, and that's a translation. However, things get a little bit tricky when you're talking about something like a chatbot, right? So if you have a chatbot, what is your input and what's your output? Like one thing that could be your input is like all of the context that you've seen before. And then your output could be, you know, the next like utterance or the next dialogue turn. But on the other hand, another way you could look at it is, well, it's all just part of this one big sequence, and we want to model this whole big sequence at a time. And so because of that, decoder-only models basically don't force you to decide what your input and what your output is. You can just treat all of it as one long sequence. And that's a little bit more convenient. Another reason why decoder-only models are a little bit more convenient is they're simpler. So they just have, you know, these two layers, and they don't have like separate multi-head attention blocks for the encoder and the cross attention and the decoder attention here. And so because this is simpler and has fewer parameters overall, you can just make each layer bigger, or you can make more layers or other things like that. Actually, one thing I forgot to mention is this NX means you do this over and over again. So you have like multiple layers of these blocks, basically. Cool. Any questions here? Yeah.
Layers are the same size and the same size.
Yep. So what do you mean by same size is the first thing to ask about. Do you mean the same number of parameters, or do you mean each block is the same size? So for the same number of parameters, I think it really depends. There was a comparison in the T5 paper where they did something like that, and I think they did demonstrate that the encoder-decoder was like slightly better, but I don't know if they exactly controlled for the size. I'd have to go back and look at that to tell you the details. But The T5 paper is actually a really, really nice paper in terms of how they explore all the design dimensions and like training objectives and stuff like that. So you could take a look at that if you want more detail. Any other questions? Okay, so let's go into the details. So my goal of this by the end is that you have a very good grasp of, you know, all of the basic components that go in here, and also some of the parts that LLaMa is changing from the original architecture and why that's important. So that's kind of the main goal for today. Okay, so core transformer concepts. As I said, positional encodings are one core concept. Multi-headed attention is another core concept. Masked attention is a core concept, which I kind of talked about last time, but I'll talk in a little more detail. Residual layers and layer normalization, and the feed-forward layers. So inputs and embeddings are kind of boring, I guess, since we've already covered them. Inputs are generally split into subwords like this, like we talked about before. Embeddings, normally you just look them up, like we discussed in previous models. So transformer-based models don't really do anything fancy here. The only big thing, I guess, is that they really, when transformer models came out, they kind of like normalized the fact that you do subword segmentation. And like every major transformer-based model does subword segmentation now. So skipping over that briefly, the next thing I want to talk about is multi-head attention, and this is kind of one of the big innovations in the transformer paper. So multi-head attention, the basic intuition behind it is that information from different parts of the sentence or sequence that you're modeling can be useful in different ways. And if you are just doing attention, with a single attention head, basically a single attention vector, you might need to make hard decisions about which part of the sentence you pay attention to. So I wrote 4 examples of the word run here. Can anybody tell me how these are different? How are 1 and 2 different from 3 and 4? Yeah, the first 2 are verbs, and the second 2 are nouns. Yeah. And so how is 1 different from 2? If you know another language, if you translate them into another language, are they translated the same or differently? Yeah, the meanings are different. So this is also called word sense, or it's called semantics, or it's called other lexical semantics or something like this. But basically the meanings are different. Like if you translate these 2 into probably many other languages in the world, they'd have a different translation because they mean different things. Like run a business versus physically run. And same for 3 and 4, right? Run in a stacking is very different than making the robber making a run for it. Now, if you look at the information, you might not even think about it, but if you look at the information you use to disambiguate these things, it's pretty different. Usually for syntactic things, you can just tell from the nearby context. So for example, if you have a noun to the left, usually that means something is going to be a verb. On the other hand, if you have a determiner on the left, it's almost certain that that thing is going to be either a noun or an adjective. So you only really need to look at very local context to do this sort of disambiguation. But in order to disambiguate semantics, you need to look at farther context. One interesting thing is, like, let's say you want to learn embeddings of words. There's actually a trick that you can use when training word embeddings where you only look at the local context and you can learn syntactic embeddings, or you don't look at the local context and you only look at the farther away context and you can learn semantic embeddings. So like you can actually use this to get like influence your models in interesting ways. But anyway, that's kind of an aside. So the basic idea here though is different pieces of context can be useful for different purposes. And that's kind of what multi-head attention is trying to get at. So it doesn't want to force you to decide whether to look at I or to look at business, but it wants you to allow you to look at both of them for different purposes. So how exactly does multi-headed attention work? I wrote the equation up here, and actually I should point out that the reference on the web page for the annotated transformer is really nice. Like I got some of the equations directly from that, and you can look through and see PyTorch code for all of these things too, which can be helpful. So anyway, we have the multi-headed attention, and it looks like this. I'm going to walk through the diagram that I have down here, though, because it might be a little bit easier to follow. So this diagram is a little bit different than what is presented in the attention is all you need paper, but I intentionally made the diagram closer to how you actually want to implement it in PyTorch, for example. So the first thing that you do is you have a whole bunch of query vectors and a whole bunch of key vectors. So the query vectors here, I only have 3 of them. The key vectors and value vectors, I have 4. That's kind of intentional. So this is permissible. You must have the same number of key vectors and value vectors, but you can have a different number of query vectors if you want. So is that clear? In which case, can you have a different number of query vectors and key vectors? Yeah. When it's masked, you could do that. Yeah, that is true. I was thinking something else. Yeah. When you're decoding and you have a short sequence and you're attending to a longer sequence, yeah. That's basically it. You can have this when it's cross attention. Because in cross attention, the sequence that you're attending to can be different than the sequence that you're using to attend. If you're doing self-attention, these need to be the same length because the sequences are the same, so the length of the sequence will also be the same. So, yeah, that's one thing. The reason why I made these different, just to demonstrate that they can be different. So the first thing that you do is you multiply by weights, and you have 3 different weight matrices. Actually you have 4 different weight matrices overall, but here we're going to use 3 of them. The first one is the query matrix. So you multiply this input by the query matrix. Then you have your key matrix. You multiply the input by the key weight matrix, and then you have the value matrix that you multiply by the weights here. And that's what we have up here in the equation. Then the next thing that we do is we split and rearrange these into n attention inputs. And so the way we do this is we split these up like this. So we have 1, 2, 3, 4. We split them up into 2 of them of size 2. So this is the case where you have 2 attention heads. And each attention head has a vector of size 2. In reality, usually your vector will be sized like 512 or 1024, and then you'll have 8 attention heads or something like this. Or much more if you have a larger model. But here I'm just doing a simple example for illustrative purposes. And we do this over all of these. Note that this is like a little bit different than the equation that you have here. So the equation that you have here, you're splitting up first and then doing the matrix multiply. So you would be doing the matrix multiply of this matrix resulting in this, then you would do the matrix multiply resulting in this. But in reality, we do the big matrix multiply all at once just because it's more efficient to do it that way, because we want to do more big operations than do a bunch of operations separately. So this diagram here is closer to what you actually do in PyTorch, for example. So this is now a 3-dimensional tensor. Like at this point here, you would have a 3-dimensional tensor where we have 2 rows and 3 columns, and the 3rd dimension is 2. So you can see it's kind of three-dimensional here. And that's also good because in the next step, we're going to run attention over each head. And when we run attention over each head, if we run attention over three-dimensional tensors once, that's a lot more efficient than writing a for loop and doing it individually over each of these split up things here. So that's that's the next thing we do. And when we run attention, we basically calculate the attention vector using the query and the key. And then we multiply the value vectors by that attention vector, take the weighted sum by the attention vector. And that gives us a result that looks like this, basically. So, of course, the number of columns in this will be equal to the number of columns in the query vector here, because we calculate one representation for each thing in the query matrix. And then we concatenate them together. And when we concatenate them together, we get a bigger vector here. And so when we do this, each one will get a different attention weight. So we have a different attention weighting over all of them. This is what the code looks like. I basically put it up here, but you do linear projections for all of these. We reshape to get H heads. We apply attention to all of the heads, and then we concatenate them back all together, and then we apply a final linear layer. So we have a final matrix multiplication at the very end here. And so I didn't really explicitly expand the attention vectors in the previous diagram, but I have them here. So this is an example from the Vaswani et al. Paper, and they're showing what happens when you calculate self-attention. And this is the self-attention values for the word making. And the self-attention values for the word making are mostly attending to like more difficult. And that really closely matches with what I talked about before, right? So run in English is kind of a verb with lots of ambiguity. Like how you translate the word run would be very different based on, the other words in the sentence. Make is also a word with lots of ambiguity. So in order to understand how you would translate it, you would need to pull in information from other parts of the sentence. And specifically, making something more difficult is different than like making a cake or making a house or something like that. And so because of that, it's pulling in lots of information from over here. But there are some attention heads that are like attending to the word itself. So this is pulling in information from the word itself. There's also another attention head that's pulling in a word from information from the previous word. So this could be one that's doing like syntactic disambiguation of some variety. So you can see that each head is pulling in different varieties of information here, which is kind of the function of multi-head attention. So yeah.
So what happens if you have a multi-head attention and the sentence is shorter than the number of heads?
What happens if you have multi-head attention and the sentence is shorter than the number of heads? So that's a good question. It's actually not a problem at all, because here, let's look at the length of the sentence. The length of the sentence here would be 3. This number of columns is the length of the sentence. Here, the length of the sentence would be 4, but we're not splitting on the columns, we're splitting on the rows. So you need to make sure that the rows are greater than the number of heads, and you always do that because you pick a representation size of something like 512, and then you pick the number of heads to be equal to something like 8. So you're sure that it's always divisible, it's always larger. There's actually something crazy called fine-grained attention that was proposed like right after attention was proposed, where you made the number of heads equal to the number of representations, but people stopped doing this just because it's it's overkill. You don't need that many attention heads. And actually in the transformer paper, they experiment with different numbers of attention heads and found 8 was like sufficient for their purposes. So, yeah.
Attention in the original paper is not causal, right? So it can like get into future tokens as well. Attention.
attention in the original attention paper from like 2014, where they first proposed attention. In the original paper in 2014, where they first proposed attention, they were doing exclusively cross attention like this. So they were attending to, like they encoded everything with bidirectional RNNs, and then they were just attending to things in the input, not like doing causal attention. Causal attention was basically, causal attention is like left to right or masked attention. There's like different ways of saying it, but masked attention was first proposed in the transformer paper, and it was, it basically was only in the output also. And then actually the first decoder only models, the first decoder only model was basically like GPT-1, like the first GPT model. And there they did causal or masked attention just on the output side. Or just modeling sequences, yeah.
So in the input to the GPT, when we say that in the making example, when we sort of looked at the self-accounts information,
Yeah.
in the decoder only model, would making not be able to attend to future tokens that comes after?
That's a good question, and basically the answer is yes. So encoder, that is one argument for why encoder decoder models might be more useful, because you can do bidirectional attention on the inputs. And there's also, so there's actually something right in the middle. It's not used super widely nowadays. But basically it's something called a prefix language model. And a prefix language model is something where you only have the parameters of a decoder, but you allow it, during training, you allow it to do either masked or unmasked attention. So you only do masked attention when you're generating, but you also like do unmasked attention also. So it's just a way to train the model. It's a small modification to how you train the model, but some papers have said that's more effective, but I guess it's like more complicated, and I don't see it used super widely right now. Yeah. The multi-head attention, yeah. The number of rows is the dimension of the word cycle. Yeah, so the reason why we don't split on the rows, so if we go back to the reason why attention is so powerful in the first place, the reason why attention is so powerful in the first place is we're applying the exact same function no matter how long the length is. So that allows us to extrapolate essentially to like infinite, like as long as we want or short as we want sentences. If we were doing things like splitting on the length of the sentence, then we would run into the problem where we had the question about before, which is like, what if the number of attention heads is shorter than the sequence length? So you could come up with a model that did something like that. You could come up with a model that said, okay, I'm going to split the first quarter of the sentence and then the next quarter of the sentence and the next quarter of the sentence. And there actually were models like that back in the day, like where people encoded different like quartiles of the sentence separately, but it becomes a little bit tricky, and like, what if it's shorter and stuff like that? So you need to deal with all these scoring cases. Yeah. Cool. Okay, any other things? These are all good questions. So. Okay, I'll move on to the next slide. Okay, so positional encoding. So this is another really core part of the transformer model. And the positional encoding goes in here. It's added together with the input embedding. And because the transformer model is purely attentional, if embeddings only are used, there actually would be no way to distinguish between identical words. So because you're just taking the input embedding, if you had a big dog and a big cat, the attention values from every other place in the sentence would be guaranteed to be the same for big, right? So you would always have the same attention value for these words because their vectors are identical. And that's a problem, I guess, because like, as I said, sometimes syntactic information needs to be pulled in from like locally coherent context. So that's a problem. A couple ways you can fix this. The first way you can fix this is use something that is sensitive to position, like an RNN. And an RNN, looks at which words came before, which words came after, and stuff like that. So that would solve your problem, but the whole point of transformers or attention is all you need is to not use RNNs. So we need another way to fix this problem. So the way this is fixed is using something called positional encodings. And so positional encodings add another embedding that's based on the word position. And so in addition to having something that's based on the word identity, you have another embedding that's based on the position. So then the word big that appears in position 2 would be embedding of big plus embedding of position 2. And the word big that appears over here would be the embedding of big and then the embedding of position 8, for example. So that kind of solves that problem. There's a number of different ways to make these. The original transformer paper, they did it using something called sinusoidal encodings. This is kind of one of the, I don't know, when this paper came out and we were first reading it, when it first came out, it was like, they explained what they did and they explained very briefly why they did it, but it was kind of like a mystery, like nobody actually understood what they wrote in the paper. Luckily now there's a lot of nice blogs that actually explain this. And so the way these work essentially is you have a sign like this, and the sign is this weight times the time step in the output. And every even numbered embedding is uses a sign. Every odd numbered embedding uses the cosine. And this omega over here is 10,000 to the 2k divided by d. And so that's the value, and then this is the dimension size. And what these embeddings look like is something like this. So sorry, this is very small, and also I should acknowledge that comes from this blog up here. But this is the position in the sentence, and then this is the embedding size, I believe. And so why did they choose to do it this way? They chose to do it this way because if you multiply these positional encodings together, you get something that looks a bit like this. And so if you multiply the two vectors together, you get something where if you're closer together in position space, you get a higher number. And so that kind of gives you a bias to upweighting the attention values of things that are closer together, at least right at the very beginning, like layers of the model where it's kind of more important because you don't have it in, information calculated from the previous layers. So this is a basic idea. I think the thing on the right is the most important thing to know here, which is like, this is the reason why they chose to do it that way. But that's the basic idea, yeah.
Previously, I think it looked at just linearly taking positional encodings, like if it makes you would multiply that factor, and then it will and so on. But I guess like, why do we need to do this complicated, not just something linear?
So, sorry, which part were you talking about with the half of the encoding?
I guess in the reading, so the position statements they talked about is if it's the word plus minus one, then you multiply it, let's say half, and then a fourth, and the eighth.
Yeah, so I'm going to talk about that in a second, actually. Any other? Okay. So this is what is done. Note that these are added right at the very beginning, and then you pass this through every layer. But basically, at the very beginning layer, at the very first layer, by using these positional encodings, you can kind of disambiguate. You can disambiguate this case here. And then after you passed it through the first layer, you're combining together information anyway. So you can have pulled in information about the local context. And now, like, it's essentially, it's essentially already handled for you. Another thing is if you have residual connections, this gets passed into the following layers, which I'll talk about in a second. So, the second thing that you could do is learned encodings. And learned encodings, basically what they do is they create a learnable embedding that you just add in. And this is super simple. So it's like just like you learned the embedding for W big, you learned the embedding for W plus 2 or plus 6. And this is simpler. Like you don't need to think about sines and cosines and stuff like that. It's also more flexible because the model can learn anything it needs to, learn in order to do a good job of minimizing the loss. But the biggest disadvantage is it makes it impossible to extrapolate to longer sequences than you saw at training time. So because you have no learned embeddings for longer sequences, it's at least in principle impossible to extrapolate to longer sequences unless you do some sort of heuristics. And if you do heuristics, you don't really know what's going to happen. So that's the disadvantage to doing it this way. In contrast, this, you just make k larger and calculate this deterministic function, and you could, theoretically extrapolate, but empirically models, even ones that use this sort of extrapolatable embedding, don't do super well at extrapolating to longer sequences. So going back to the question, there's a distinction between absolute versus relative positional encodings. And absolute positional encodings are like what I said before. They're basically positional encodings where you add in you specifically add in an encoding at each position, but you don't consider whether like one query vector is close to a key vector or far away from a key vector or anything like that. You don't consider that directly. On the other hand, relative positional encodings explicitly encode the relative position. And so what this means is when you do attention, it explicitly thinks about whether, a particular embedding is not in position 8, but whether the key embedding is like -5 from the query embedding or -8 from the query embedding. And the first paper that did this, they just learned relative positional encodings, and they learned it. If I remember correctly, they basically learned a scalar where you're centered at 0, and then you have like minus and you have minus and plus a certain distance, and then you also cut this off at minus 128 and plus 128 or something like this. So you have a fixed length vector, and anything that's farther away from that gets the same embedding basically. The problem with this is number one, it adds learnable parameters. Number two, it's a little bit more computationally expensive to apply this every time onto your attention matrix. And because you need to apply this at every layer. You need to apply this every time you do attention at every layer. So instead, there was a really clever idea called rotary positional encodings. And rotary positional encodings are basically kind of like an absolute positional encoding with a lot of the desirable qualities of relative positional encodings. And their basic idea was this. So their basic idea was that they wanted to come up with something where you have an embedding encoding vector that takes in the actual vector and the position. And you have another encoding vector where you take in the absolute vector and the position. And the product of these two becomes another function that is a function only of the two vectors and the relative position. And so you lose all information about the absolute position. You only have information about the relative position. And this is trickier than it seems, basically, because like you need to have something where it's not possible to recover the absolute position, because you want it to rely only on the relative position, because that will allow it to extrapolate well. That will allow it to generalize well when you see new outputs. So basically what they do is they do a lot of math that I'm not going to cover in a lot of detail here. But by using imaginary numbers, trigonometry and imaginary numbers, you can essentially come up with a thing where you have the query vectors and the key vectors, I believe. I think I might have that backwards. I'll have to check that. But basically, you take the vectors, one of the vectors, and you add in the cosine m theta 1, where theta is a parameter similar to the omega parameter that we had before. M is the time step, the position in the sequence. And then you, on the other side, you have sine and m theta 1 over here. And then you swap around the order, like minus, and you invert the score here, invert the embedding here. And if you do this, you can prove that essentially you get a function that has this property. And so by doing this, you're only adding, you're modifying these directly, but you're getting some of the nice properties of positional encodings. And you're also kind of guaranteed that this will extrapolate infinitely, because you're removing all information about the, not entirely infinitely, but you're guaranteed that this will extrapolate well, because you're removing all of the information about the absolute position here. So this is what's actually used in LLaMa. So this is what's used in LLaMa, and it has a good positive effect on fitting models in various senses. Yeah.
Going back to the kind of the visualization,
Yeah.
considering, further down the sentence, the embeddings look very similar.
Yeah.
So is this kind of embedding more sensitive to something at the beginning of the sentence than at the end of the sentence?
I don't know if it's more sensitive to tokens at the beginning of the sentence and the end of the sentence, partly because the earlier ones don't look like, I mean, the ones at the beginning also look similar, right? Like all of these values are the same. Like all of the values up here are the same between 1 and 2, right? So the ones at the beginning of the sentence also look similar. The ones at the end of the sentence also look similar.
So if you have something at the different pages and
Yeah.
at one time page,
Yeah.
embedding looks valid.
Not really, because the things at the beginning look different, right?
Oh, probably with reading the
Yeah, so this is the position. Yeah, okay, yeah, sorry, this is very small because I just grabbed it from this this blog post here, but yeah, this is the position, and then this is the embedding size. Yeah. Okay, yeah, but this is really, really important. This kind of change of the positional encodings, and I'll talk a little bit about that at the very end. Yeah.
Does rope not take any sort of like maximum context length or anything like that?
Rope, so this does not have a maximum context length. This actually also doesn't have a maximum context length, but rope extrapolates better, because you basically, in rope, you entirely lose information about where you are in the sequence. Whereas the absolute positional encodings, you still get the information about where you are at the sequence, so the model can overfit to it better.
Professor, in this example, when we want to sort of like fit this to a longer sequence, we have to modify the K to get it to it.
You do, You do not.
Oh, we don't.
Yeah, so this K is the size, this is the size of the embedding.
Okay.
So you can extrapolate by just increasing T. Beyond, like, even if you've never seen something of that T, if you increase T, you can still calculate this theoretically, which is not the case for the learned encodings. So learned encodings, you don't have any information about that. Okay, cool. So this is an important thing to know. You'll also have to implement this for the assignment, I believe. So good thing to pay attention to. Okay, next is layer normalization and residual connections. So layer normalization and residual connections are important for stabilizing training in transformers. And I talked before about RNNs with gradients and training instability. So in RNNs, we saw how backprop, we talked about how backprop can reduce the gradients. The exact same thing would be the case for transformers. And in fact, there was a problem in the original formulation of the transformer that caused this gradient vanishing to occur. And this problem has been rectified in newer versions of transformers. So I'll talk a little bit about both of those. So because we're running this multiple times, we have 8 layers of transformers, or 16 layers of transformers, or 12 layers of transformers. We do have gradients disappearing at the beginning if we're not careful. And so there's 2 things that people do. The first thing is layer normalization. And what layer normalization does is this is not so much for like gradients disappearing, it's more for preventing gradients from exploding or becoming very unstable. And the way it works is it normalizes the outputs to be within a consistent range, preventing too much variance in the scale. So the way layer norm looks like is this. And it's not too complicated, but it's a little bit of a complicated equation. So I'll go through it one at a time. The first thing is we take the mean of the vectors. So we just add up all of the vectors and we divide by the number of vectors that we have here. Or sorry, the number of elements in the vector that we have here. The next thing is the standard deviation of the vector. So we add up the value minus the mean squared and then take the square root of it, just normal standard deviation. And so if we were just doing the vector mean and the vector standard deviation, what we would be doing would be, we would be normalizing all of the values in the vector to have 0 mean and unit variance. And divided by the standard deviation. However, layer normalization does 2 other things also. So layer normalization adds in a bias and it multiplies by a gain. And what adding in the bias and multiplying by the gain means is after we've normalized everything down to be kind of in a standard range, we then move it out of the standard range. So we're taking like this vector from over here, we're normalizing it down. So it's centered. So this is using the mean and the standard deviation. We're normalizing it down. And then we're adding a bias and a gain. So now we're moving it over to be in like a standard place. So what that means is, like, let's say we got a new vector. Let's say this is x1. Now we got a new vector, x2, and it's over here. We would normalize it down and move it up here again. So like basically all of our vectors will be in a consistent part of the space. And what part of the space and how big the spread is will be determined by the bias and the gain. So that's essentially what's happening here. And what that means is, like, every time you consume the output of a layer normed layer, you get something predictable. You get something in a predictable part of the space. So that's what it's doing. And this is good for training stability. Any questions about this? Okay. Yeah.
You just like what's the difference between this and batch learning?
So the difference between this and batch norm, this is actually explained really well in the layer norm paper, but what batch norm does is it normalizes not over the whole layer according to all of the elements of the vector, but over the whole batch according to all of the elements in the batch. And the reason why, so batch norm, I think a lot of people really didn't like it when it was really popular to be used, because batch norm actually changes your statistics based on the other elements of the batch. And also at inference time, when you're doing something at inference time, basically you don't have any other statistics from the other elements of the batch, so you just have to do one and you can't do any normalization. Layer norm only depends on the current instance. And because layer norm only depends on the current instance, you don't need to worry about batches. Like every input and output is like constant, no matter what else is in the batch. So that's a basic difference. Any other questions? Okay. So there's also a improvement to layer norm called RMS norm, or root mean square normalization. This is basically just a simplification of layer norm. And what they did is they removed the kind of mean normalization step. So instead of moving everything into the middle and into a different part of the space, they're just keeping things in the same part of the space, but renormalizing like the gain, renormalizing the spread between them. So what you can see is, like, if you look back at layer normalization, we were calculating the mean. Here we don't have any mean calculation. Here we're subtracting the mean. Here there's no subtraction of the mean. So that's basically the difference between the two. And it's not that RMS norm is any better, really. Like it gives similar results to layer norm, but it's faster and empirically not very much worse. And so because of this, this is used for efficiency. And this is used, this is also used in LLaMa. Also you remove the bias parameter and you keep only the gain parameter. So that also reduces the number of parameters. Cool. Any questions? All set? Okay. Residual connections. I talked about these a little bit last time, so I'll go through them relatively quickly, but they're basically an additive connection between the input and the output. And so you take the input to multi-head attention and you pass it into the output here. And it looks like this, very, very simple. So no matter what function you're doing here, you just add the input into the function. This prevents vanishing gradients, and it allows you to learn the difference from the input. So instead of learning how the input should be mapped into the output, you learn what difference should I apply to the outputs. So here's an interesting quiz. There's a very big implication for attention, for multi-head attention. Can anybody think of what the big implication is for multi-head attention here? Yeah.
Because we now have the residual connection, it sort of deprioritizes looking at itself.
Yeah.
It looks at the surroundings to understand what do I have to add as context.
Yeah, exactly. So basically it deprioritizes attending to yourself because you get yourself for free through the residual connection. You get the information from yourself for free. So you just need to pull in the other information that's useful for contextualizing the current vectors. And you can actually see how this actually happens. If we go back and look at our visualization, you'll notice that there's only one attention head that's attending to itself, and all of the other attention heads are not attending to itself. And this is precisely because you have the residual connections. If we didn't have the residual connections, it would have to attend to itself heavily and then pull in like all of the other information. So that's why you see that behavior there. Cool. I didn't expect somebody to answer that so quickly, so thank you. Another really important improvement to the transformer is post and pre layer norm. So the original conception of the transformer basically had this over here, post layer norm. So what you would do is you would run multi-head attention, then you'd have layer norm after it. Then you have the feed forward network, then you'd have layer norm after it. The problem with this is kind of breaking the residual connection, right? You see, we have this residual connection, which is gray here, and then you have a layer norm in the middle of this residual connection. And so what this is doing is this is actually hurting your gradient propagation, right? Because you have a function other than the identity right in the middle of the layers here, and that's bad for propagating across many layers. So a modification to this is pre-layer norm, where basically layer norm is applied previously to all of the like multi-head attention and feed forward layers, which gives us a like direct residual connection like this, all the way from the beginning to the end, and that improves gradient propagation. So this is another big thing that has improved the training of transformers and made them more stable and other things like this. Yeah.
Professor, can you elaborate more on like why having layer norm between the layers is worse for gradient propagation? I couldn't really understand that.
Yeah, sure. So basically anything other than the identity is bad for gradient propagation because the identity function or addition of some other piece of information doesn't change the gradients that flow back through the network. But anything other than that does, right? It either makes them smaller or bigger or modifies them in some way. How does layer norm modify them? Layer norm modifies them by the standard deviation. So like, let's say the standard deviation in the layer is quite large and your gain, and especially if your gain is small, then that would mean that you were dividing every time by the standard deviation, which would make the gradient small. So it's pretty like straightforward actually. Yeah. Yes. So you're basically right. Like if we apply something like tan H, then the gradient would disappear. I'm actually going to talk about activation functions, and usually we use activation functions that don't have that problem quite as much. But the other thing to point out here is actually the residual connection is going all the way up, and it's not like the feed-forward network is being applied like outside of the path of the residual function. So essentially the gradients will be vanishing because the feed-forward network is not blocking the residual, like the residual path from the beginning to end. So, does that make sense? Another way to put it is this will be like the tan H will be inside this function, but you're separately adding in X outside of that tan H, so you don't lose gradient. Cool. Any other things? Okay, great. So this is also really important. This causes the models to work better. So next is feed forward layers. So the feed forward layers here, what they do is they extract combination features from the attended output. Basically, the feed forward network is applied independently to each vector in the sequence. And so like if we have our vector, here, we apply it like this, like weight 1 and B1, weight 2 and B2. Actually, it's pretty common nowadays to remove the bias also, mostly because it's just extra parameters and not useful, and it can be more, it can lead to some degree of instability in training. So you'll often see linear layers that have the bias off, and it's just because it's not necessary to learn the network well. But anyway, this is what it looks like. F here is a nonlinearity of some variety. So it essentially looks like this. Usually the feed forward network in transformers upscales to a very large vector to extract lots of features. So each one of these elements in here is kind of a feature. And a lot of people, when they do interpretation of transformer models, they actually look at these features because they tend to correspond more directly with kind of the information that we would expect to see. Like, for example, when people memorize individual memorized facts in transformers, like who is the president of the United States or something, they usually look at the vectors in here. Some activation functions that are used in transformers. The original transformer used a ReLU. So the ReLU looks like max 0 of x. I asked ChatGPT to draw a figure for me, and it did a pretty good job of this, I guess. So this is what it looks like. The ReLU is 0 below an input of 0, and the identity greater than an input of 0. The problem with this, though, is anytime something is less than 0, you get a 0 gradient. So it causes issues. So an alternative that's used recently is something called SWISH, or CMU for sigmoid linear unit. And basically it looks like this. It's x times sigma times beta, where beta is often set to 1. And it looks a lot like a ReLU. It looks very similar to a ReLU, but it doesn't have a 0 gradient anywhere. So you can still, if it gets to be very negative, you have like a light push. You have a light push towards the middle. So you have a chance to recover and get things closer to the middle. So empirically, this seems to work pretty well. And this is also used in LLaMa. Cool. Any questions about these? There's, of course, a ton of other activation functions, but I am talking mostly about the ones that people are actually using. Usually you just set it to 1 or set it to some. You could hyperparameter optimize over it, but I think it doesn't make a huge difference. Yeah. Okay, cool. Next is optimization tricks for transformers. So transformers are powerful but very fickle. Transformers, at least when they started out and we didn't have stable training recipes for them, tended to be very, like people tried pretty hard to optimize them, but they were difficult to optimize. One example of this that is really great, it will make you feel a lot better if you're training things and they're not working very well, is Meta's old logbook of how they trained a 175 billion parameter model. And you'll see all of the problems that they had while they were training their model, despite the fact that they're kind of pros at doing this. And that includes things like their machines going down and their like hardware engineers having to go and resurrect their machines, and their loss diverging and having to roll back things manually and other stuff like this. So I really like this. I'm really happy that they released this for us all to learn from. But yeah, you can take a look at this. So some things that people do to stabilize training of transformer models are swap out the optimizer, do the sorts of restarts that I talked about, and other things like this. So I'm going to go through those very quickly. So the first thing is optimizers. Previously, what we've talked about is SGD. So SGD updates in the direction of reducing loss. Atom, which I also talked about, adds a momentum, sorry, that should be term, momentum term, and normalized by the standard deviation of the outputs to kind of upweight infrequently updated parameters. A new thing that was introduced by Vaswani et al. When they introduced transformers was a learning rate increase and decrease. And the way this works is they gradually increase the learning rate until you get to a set number of warm-up steps. And theirs, they did 4,000 warm-up steps. And then they gradually decrease it. And it looks like this. Recently, as far as I understand, you can actually do a bit better without doing this warm-up as long as you're using pre-layer norm. So I think the warm-up is still used pretty widely, but it's not absolutely necessary anymore with the newer training recipes, but it's something to be aware of. Also, sometimes people do linear learning rate decay instead of this kind of like sloped learning rate decay. So there's a bunch of recipes for this. I'm not going to go into all of them, but just be aware that they exist. Another thing is instead of straight up atom, recently people have been using atom W. And so what atom W does is it does weight decay. And what weight decay is it like gradually decreases your weights towards zero. And the reason why you do that is it's like basically an approximation of normalization of regularization of the models. So it has an effect of preventing the model from overfitting. Atom W is kind of you don't need to know all the details if you're just using it, but it's basically a correction of weight decay, specifically considering the fact that atom is using momentum in this normalization so that it actually corresponds to a proper regularization term. So if you're just using atom W out of the box as an optimizer, that's all you need to know. But actually, sorry, never mind. For the assignment, you're actually going to have to implement something related to that. So you do actually need to know it and look into it. I'll maybe cover the details in a later class. But, okay, cool. Another thing is low precision training. So low precision training is something that's necessary when you're training very large models or large-ish models on fewer GPUs. So training at full 32-bit precision can be costly. So it's pretty common to train at, for example, 16-bit precision, especially if you're training all of the parameters of the models. And there's kind of two alternatives for this. The first one is FP16, and that's the standard 16-bit floating point numbers that are used by most computers and most CPUs. And these floating point numbers, they allocate 1 bit for the sign, 5 bits for the exponent, and 10 bits for the fractional component. So they have relatively precise fractions and exponents with a relatively small range. So they can't express things with very large or very small exponents. There's something called bfloat16. In bfloat16, B stands for brain, for like Google Brain, because that's where they invented this. And basically what it does is it increases the number of bits for the exponent to 8, and it decreases the number of bits for the fraction to 7. So that allows you to express a wider range of values at a lower precision, essentially. And this is much, much more stable with respect to training because you can handle very small numbers and very large numbers better, despite the fact that you're losing a little bit of precision on the fractions. So this is pretty essential, and I would recommend that no matter what you're doing, if you're doing 16-bit, you would use this instead. And hardware support for this is pretty good now, like NVIDIA GPUs and other things like that. I'll support it. Piper supports it really good. Another thing that you should be aware of, especially if you're training very large models, is checkpointing and resets. So even through best efforts, training can go south. It can have problems. So what do? The first thing that you can do is you can monitor for possible issues. And a common way to do this is by monitoring the norm of the gradients. And so I pulled this directly from the OPT logbook that I posted before, the thing that Meta did when they were training their models. And here you can see you're monitoring the norm of the gradients. And suddenly, like in the middle of training, your gradient norm just goes up by a lot or something. And this is an indicator of a problem. But the interesting thing about this is this will spike. And then after it spiked, you can see that the perplexity of the model is going down. After the spike, it continues to go down for a little bit, but then it starts going up. And so basically, once it starts going up, now your model is kind of in like a bad space. It's in a bad space of the parameter space, and it will just continue being in a bad space until it diverges. But it's hard to diagnose immediately other than through things like the gradient norm. So monitoring the gradient norm can be helpful. This is especially important if you're training very large models. If you're training smaller models, it's not as big of a problem. But this is something to pay attention to. If training crashes, what can you do? So a very common thing to do is to roll back to a previous checkpoint, like save out checkpoints periodically. Roll back not to right before the gradient spiked, but roll back to, like 100 steps before the gradient spiked. Shuffle your training data set or jump to a different part of your training data set and resume. So this is a very like hacky thing to do, I guess, it seems, but by doing this, you're injecting some randomness in the process by looking at different data, and that can cause your model training to stabilize. There are even some platforms that do this automatically. Like I think the Mosaic ML platform does this automatically and fixes this for you. So another thing though is you should also be checking your code. And ideally, if you have really solid code that doesn't have any sort of dangerous functions in it, and also your learning rate is set appropriately, this happens much, much less. So if your model training is spiking all the time, then this could be an indicator that you have a problem. And just to give an example, like, let's say you're taking an exponent, let's say you're taking the log of something where you're pretty sure that this should be positive. You're taking the log of something where you're pretty sure that this should be positive, but in fact, it's getting very close to zero some of the time. So if it's getting very close to zero some of the time, you'll get a huge gradient because like log zero has an infinite gradient, and things that are very close to zero have something very close to an infinite gradient. So usually if you're seeing these sorts of spikes, there's a reason for them like this. So you can also try to diagnose and make training more stable. This is kind of a, like, this is a good thing to look at, but there's a lot of like experience that goes into this. So just going in and diagnosing and digging into the code is a good way to level that. Cool. Any questions? Any questions about this? I think a lot of this is like lived knowledge. So just, try it. And if you have problems, ask me or the TAs or people. So the final thing I'd like to talk about is comparing transformer architectures. So I talked about a lot of design decisions. I'm not going to talk about every single model today because I want to do that a little bit later after we've introduced more concepts. But I would like to at least compare the Vaswani et al. Paper and LLaMa. And if we look at some of the differences between them, they're both using transformers. They're both doing a lot of things similarly. But some of the differences are what is the norm position? Vaswani et al. Is doing post-norm, LLaMa is doing pre-norm. What is the norm type? Vaswani et al. Is doing layer norm, LLaMa is doing RMS norm. What nonlinearity are they using, ReLU versus SILU? And what positional encoding is sinusoidal versus rho? And you might be asking me, you might be thinking like, well, how much do I care about this anyway? I mean, like it, might not be super important. But there was actually a really nice paper by Albert Gu, who is an assistant professor in MLD, where they were proposing a new architecture. But one of kind of the Easter eggs in this paper is this comparison here. And in this comparison, they basically compare the Vaswani et al. Original transformer architecture and the LLaMa style, like transformer plus, like good transformer architecture. And they compare the perplexity, or actually this is log scale perplexity. So it's basically like negative log likelihood on, oh no, sorry, this is perplexity, but it's on the log scale. So yeah, this is actual perplexity. And then they compare the perplexity based on the number of training flops. And so if you look at the yellow transformer and the orange transformer plus, you can actually see that it takes 10 times more flops to achieve a approximately similar, it can take 10 times more flops to achieve an approximately similar result with the old architecture compared to the new architecture. So this is like really, really important, right? You want your training to be 10 times faster. So you can see that like a lot of people were saying like scale is all you need and architecture engineering isn't important or things like that. But it turns out that architecture engineering is kind of important. So like a lot of the advances we've made in the past 5 years or 7 years with respect to that are actually making a big difference. Cool. So I'll leave it at that.